Welcome to the deep dive, where we cut through the noise to get straight to the knowledge you need. You've probably heard of Bitcoin, right? It delivered the first truly decentralized digital currency, kind of shifted our understanding of money. But what if that same underlying technology, the blockchain, could be used to build anything digital, not just currency? What if it became like a global computer, a platform for, well, limitless possibilities? Today, we're taking a deep dive into the foundational document for just such a vision. The Ethereum white paper, originally penned by Vitalik Buterin back in 2014, this document lays out a revolutionary concept, a global computer, a platform for smart contracts and decentralized applications. Our mission is to unpack its core ideas, see how it builds upon and radically departs from Bitcoin, and explore the vast possibilities it opened up. Get ready for some serious aha moments.
It really is a remarkable document.
Yeah.
Because it articulates this leap in thinking. It took Bitcoin's core innovation and just generalized it, moved beyond just a digital currency to propose a programmable layer for an entirely new kind of internet, where logic and agreements could be executed with, well, unprecedented trust.
That's a powerful way to put it. Let's kick things off with Bitcoin. It burst onto the scene, 2009? Gave us the first digital asset without central control, no collateral, no intrinsic value, a massive innovation for money, no doubt.
And here's where it gets really interesting. While Bitcoin as a currency was groundbreaking, the underlying blockchain technology itself was arguably the even more significant breakthrough. It provided a practical instrument for distributed consensus. Concepts like decentralized digital currency, property registries, that existed for decades. Think Wei Dai's B-money or Hal Finney's reusable proofs of work. But they always lacked a robust decentralized consensus mechanism to actually make them work without, a central authority.
Right. And Bitcoin's elegant solution to that was proof of work, POW. For listeners, maybe just briefly, what's a Sybil attack and how does POW stop it?
Sure. So a Sybil attack is where one bad actor tries to swamp a network by creating tons of fake identities, fake nodes. Bitcoin's proof of work prevents this by making participation costly. It ties it to real-world computing power. To add blocks, you have to spend energy, use hardware. It makes it basically impossible, or at least economically infeasible, to generate enough fake power to take over. It's a really clever way to get trust in a trustless setup. And just quickly, alternatives like proof of stake, PS, have come along since then too.
Okay, so technically then, how does Bitcoin actually manage its ledger? You mentioned it's like a state transition system?
Precisely. Yeah, you can think of a cryptocurrency's ledger, like Bitcoin's, as this continuous state transition system. There's a state, basically the record of who owns which Bitcoins, and a state transition function. That function takes the current state plus a transaction and spits out a new state. Think of your bank account. Your balance, that's the state. You send money, that's the transaction, and the bank system updates your balance and the other person's. That's the new state.
And in Bitcoin specifically, how is that state defined? What is it?
In Bitcoin, the state is the collection of all unspent transaction outputs.
Right.
UTXOs, you'll hear them called. Each UTXO has a specific value and an owner, tied to a cryptographic address. So a transaction uses existing UTXOs as inputs. You prove ownership with a signature, and it creates new UTXOs as outputs. And this process inherently makes sure value is preserved. The outputs can't be worth more than the inputs, except for that new mining reward, of course.
Right, you can't just magic coins out of thin air. And that brings us to mining. Absolutely key to updating this state. How do miners fit in? What's their role in keeping things secure?
Miners are constantly working to create blocks, these bundles of recent transactions. The network aims for a new block roughly every 10 minutes. Each block has a timestamp, the proof of work nonce, a link to the previous block, and all the transactions. This chain of blocks forms the blockchain. It's this persistent, always growing record, and security is paramount. The proof of work difficulty makes it incredibly hard for a malicious actor to rewrite the chain. That's the 51% attack people talk about. It would just require an insane amount of computing power, more than the rest of the network combined. Basically infeasible for one entity.
Got it. Speaking of Bitcoin structure, I remember the white paper mentioning Merkle trees, something about scalability. How did they help?
Merkle trees. Yeah, they're really ingenious. So all the transactions in a block get bundled into this efficient tree structure. The block's hash is actually just the hash of the header, which includes the root hash of this Merkle tree. And the crucial insight here is that this lets light nodes, SPV clients, simplified payment verification check if a specific transaction is in a block without downloading the whole blockchain.
Okay, so they don't need the entire history, which was getting big even back then.
Exactly. It was like 15 gigabytes in 2014, growing fast. Light nodes only needed the block headers and the specific branch of the tree for their transaction. It was a brilliant piece of foresight for keeping Bitcoin usable on smaller devices and maintaining decentralization. It definitely influenced later designs.
So Bitcoin gives us this amazing decentralized money system, robust, verifiable. But pretty quickly, people started asking, can we do more with this tech, beyond just money?
Totally. Even before Bitcoin, folks like Nick Szabo had ideas about secure property titles, but the tech wasn't quite there. After Bitcoin, we saw this burst of activity. Namecoin back in 2010 was one of the first, basically a decentralized DNS, a way to register names on the blockchain.
Like a blockchain domain name system. That's pretty cool.
Yeah. Then you had things like colored coins. The idea was to color specific Bitcoin UTXOs to represent other assets, like custom tokens or shares. And metacoins were protocols built on top of Bitcoin, using Bitcoin transactions to store data for other applications.
But I'm guessing there was a catch, a problem for developers trying to build these things.
Oh, absolutely. A huge dilemma. If you wanted to build something really new, you either had to launch a completely separate blockchain, which is super complex, expensive, and really hard to secure initially, or you build on Bitcoin using these meta protocols. But that had downsides too. Often you lost that nice lightweight verification feature, the SPV. Many ended up needing trusted servers or intermediaries, which kind of defeats the purpose of decentralization, right?
Yeah, it brings back the middleman.
Exactly. So that limitation was a real bottleneck. It stopped blockchain tech from easily moving beyond just currency.
And this leads us nicely to Bitcoin's scripting language. It did allow for some basic smart contracts, like multi-sig needing multiple keys for a transaction. But the white paper really highlights its limitations. What were they?
Yeah, the limitations were significant. The biggest one was simply a lack of Turing completeness, basically no loops. This made writing complex logic either impossible or incredibly clunky and inefficient. Imagine repeating code hundreds of times. It also suffered from value blindness. Scripts couldn't easily manage or be aware of the specific amounts being sent, which you'd need for things like financial contracts, hedging, and crucially, there was no real state beyond spent or unspent. A UTXO couldn't remember anything internally for, say, a multi-step agreement.
And it couldn't even see blockchain data, like timestamps? That seems limiting for gambling or anything time-sensitive.
That's exactly. Blockchain blindness. So what this all boils down to is Bitcoin was fantastic for money, but too rigid for general-purpose applications. And it was precisely these constraints that Ethereum set out to solve. It created the opening for a different approach.
Okay, let's unpack Ethereum's core vision then. It wasn't just another crypto. It aimed to be an alternative protocol for building decentralized applications, or dApps. The goal seemed to be faster development, better security for smaller apps, and easier interaction between apps, a real platform.
And the core, the really big idea, was revolutionary. A blockchain with a built-in, Turing-complete programming language. This meant anyone could write smart contracts with basically arbitrary rules for ownership, transaction formats, state transitions, whatever you could code. The white paper even boasts you could build a Namecoin clone in 2 lines of code, or a whole custom currency in under 20. That's a massive leap in programmability.
Wow.
Yeah, moving from like a specialized calculator to a general-purpose computer built on a blockchain.
And instead of just UTXOs, Ethereum introduced this different concept, accounts. Can you break down what these accounts are and the role of Ether?
Right. So in Ethereum, every account has an address, but also 4 key fields. A nonce, which is just a counter for transactions from that account, an Ether balance, its native crypto holdings, then potentially contract code, if it's a smart contract account, and finally its own persistent storage, like its own little database. Ether is the network's native cryptocurrency. It's often called crypto fuel because its primary use is paying transaction fees, paying for computation. And there are 2 main kinds of accounts. Externally owned accounts, EOAs, which are controlled by private keys like your typical Bitcoin address, and contract accounts, which are controlled entirely by their code. They act like autonomous agents, really. They wake up when they get a message, run their code, read, write, storage, send other messages.
Okay, so a transaction coming from an EOA includes the usual stuff like recipient, signature, Ether amount, but also an optional data field, right? And start gas and gas price. That gas system sounds absolutely critical, especially with a Turing-complete language where things could potentially run forever.
Oh, absolutely critical. Yes. The gas system is Ethereum's ingenious solution to the denial of service problem. Because the language is Turing complete, someone can write a contract that just runs in an infinite loop, trying to bog down the network. Gas prevents this. Every computational step costs a certain amount of gas. The transaction center sets a maximum amount of gas, or gas they're willing to pay for, and a price per unit, gas price.
If the transaction runs out of gas before finishing, it just stops, halts execution. But, and this is crucial, all state changes made by that execution get rolled back, reverted, except for the fee paid to the miner for the gas used up.
So the network is protected, and the miner still gets paid for the work done, even if the transaction fails. Exactly. It neatly sidesteps the halting problem by making infinite loops economically non-viable. It turns this computer science challenge into an economic solution for network security. It's really quite elegant.
And messages are similar, but they're sent between contracts, also having a gas limit for their execution chain.
Correct. The overall Ethereum state transition process is pretty clear.
Yeah.
Validate the transaction, check the signature, calculate the fee, deduct it, initialize the gas counter, transfer the Ether value, and then if the recipient is a contract, execute its code using the provided data and the available gas.
And again, that crucial point. If execution fails, not enough Ether, runs out of gas, invalid instruction, all the state changes from that execution are reverted.
Right.
Except the miner fees. The network state remains consistent.
Precisely. The miners get paid for their computational effort, but failed or malicious code doesn't permanently mess up the contract states. Now, the heart of these smart contracts is the Ethereum virtual machine, the EVM. It's a low-level, stag-based bytecode language. Think of it like the CPU instruction set for the Ethereum world computer. When code executes, it has access to 3 types of memory. The stack, which is temporary, like scratch paper. Memory, which is a temporary byte array, also gone after execution. And most importantly, storage. This is the contract's long-term, persistent memory. It's a key value store that stays with the contract across transactions.
That persistent storage is the big difference from Bitcoin's UTXOs, allowing contracts to actually remember things.
Exactly. It's what enables complex, stateful applications.
Okay, what about the Ethereum blockchain itself? Similar to Bitcoin, but with a key difference you mentioned. Blocks contain the current state somehow. That sounds like it could get huge. Is it inefficient?
That's a really good question. And yeah, storing the entire state tree in every block sounds incredibly inefficient. But Ethereum uses a clever data structure, building on Merkle trees, called a modified Patricia tree, or TRI. Think of it like a highly optimized index. When the state changes, you don't rewrite the whole index. Most parts of the tree structure remain identical between blocks. You only need to update the specific paths that changed, and you can reuse unchanged parts via pointers. It's very efficient for making small updates to a large state.
Okay, so this Patricia tree structure means updating the state root in the block header is actually manageable. And does it mean, theoretically, nodes don't need the entire history, just the latest state plus the blocks?
That was the idea, yes. Full nodes could potentially prune old historical states, keeping only the recent state and block headers, saving a massive amount of storage compared to Bitcoin's need to store every single transaction forever to validate the current UTXO set.
That's a pretty significant architectural difference.
It is. And importantly, the execution of the contract code isn't separate. It's part of the block validation process. Every node validating a block also runs the EVM code for the transactions in that block to ensure they reach the same resulting state root hash. Consensus includes computation results.
So we've got this powerful world computer. What kinds of things did the white paper actually imagine people doing with it? What applications?
Oh, the scope was incredibly broad. The paper breaks them down into a few categories. Financial applications were obvious. Creating custom currencies, tokens, financial derivatives like hedging contracts, more complex savings wallets, even things like digital wills. Then semi-financial ones, where money is involved but it's not purely financial. Think self-enforcing bounties for solving computational problems. And then purely non-financial uses like online voting systems or decentralized governance structures. The possibilities seemed almost endless.
Can you give us a few concrete examples, like how would a token system actually work?
Sure. Token systems are surprisingly simple at their core. A basic contract just needs a mapping of addresses to balances. The code would just check if the sender has enough tokens, subtract from their balance, and add to the recipient's balance. Maybe just a few lines of Solidity or Viper code. You could even design it so the contract holds some Ether and pays the gas fees for users, maybe deducting the cost in its own token.
Okay, clever. What about those financial derivatives, like stable coins? How would that work without a central bank?
So imagine a hedging contract. Alice wants to hold value equivalent to $100, but only has Ether, which is volatile. The contract relies on a trusted data feed. Another contract may be updated by reputable sources like exchanges that provides the current ETH price. Speculators like Bob could lock up Ether in the contract. If Ether's price drops, the contract uses Bob's lock Ether to ensure Alice still holds $100 worth. If it rises, Bob profits. It essentially creates a stable value asset backed by a decentralized pool of collateral and market incentives, rather than a single issuer. A big step up in trust infrastructure.
That is a huge leap. What about non-financial stuff? Identity? Maybe decentralized storage?
Yeah, identity systems are a natural fit. A simple Namecoin-like registry is easy. A contract mapping names to addresses or other data. Register, name, value, done. You could build much more complex reputation systems on top of that. And decentralized file storage, that was a really cool idea mentioned. Imagine a sort of decentralized Dropbox. A contract could manage payments to users who offer up their hard drive space. Users would have to periodically prove they're still storing the data, maybe using Merkle proofs on file chunks.
Renting out your hard drive space for crypto, that must have sounded like science fiction back in 2014.
Oh, absolutely. Pure sci-fi for most people then.
And the really big, ambitious vision, DAOs. Decentralized Autonomous Organizations. What was the idea there?
DAOs. Yeah, these are essentially virtual entities governed by code and stakeholder consensus. Members or shareholders vote on how funds are spent, or even how the DAO's code should be updated. Think of it like a company or community run entirely by smart contracts. They could use rules like a 67% majority vote to make decisions. And concepts like liquid democracy, where you delegate your vote to someone else, become possible. The white paper even discussed how DAOs could achieve code mutability, the ability to change even though contract code itself is immutable.
How?
By having the main DAO contract store the addresses of other contracts that contain the actual logic. To update the logic, the DAO just votes to change the address pointer in its storage to point to a new contract version. Clever workaround.
Very clever. So the possibilities range from crop insurance using weather data feeds to peer-to-peer gambling, prediction markets, verifiable cloud computing. Just a huge landscape. But with such ambition, there must have been some serious design challenges and concerns they had to think through.
Absolutely. The white paper addresses several key ones. One was related to mining and block times, the Ghost protocol. You see, if you have a very fast block time, you get more orphan blocks or uncle's blocks mined around the same time that don't make it into the main chain. This wastes mining power, reduces overall security, and can actually favor large mining pools, leading to centralization. That's a problem.
Right, wasted effort and centralization risk. How did Ghost help?
Ethereum used a modified version of Ghost. The idea is to include these uncle blocks in the chain calculations. The block that includes an uncle, the nephew, gets a small reward, and the miner of the uncle also gets a reward, though slightly less than a full block reward. This makes the network more efficient by incorporating that otherwise wasted proof of work, boosts security, and helps mitigate the centralizing pressure on mining pools. It makes it fairer for smaller miners.
Okay, that makes sense. What about transaction fees? Bitcoin mostly relied on voluntary fees, but the white paper seemed critical of that, mentioning a tragedy of the commons. What's that?
Right. The tragedy of the commons idea here is that every transaction imposes a cost, computation, bandwidth, storage on every node in the network. If fees are voluntary or too low, senders, or miners including transactions, don't bear the full cost they impose on the network. They might overload it because it's cheap for them individually. Ethereum's gas system directly tackles this. By forcing the transaction setter to pay for all resources consumed, it aligns incentives. You pay proportionally for what you use.
So gas prevents spam and ensures resources are paid for.
Exactly. And Ethereum also introduced a dynamic block size limit, technically a block gas limit, that adjusts based on network usage using an exponential moving average to help manage overall load without hard forks.
If you touched on Turing completeness and the risk of infinite loops, the halting problem, can you just remind us how start gas elegantly solves that in practice?
Yeah, it's worth reiterating because it's so central. The start gas limit means any execution, even an infinite loop, will eventually stop when it runs out of gas. And crucially, the state reverts, but the fees are paid. This disincentivizes attacks because they cost the attacker money but achieve nothing on chain. It also protects legitimate contracts from getting stuck in some weird, inconsistent state due to bugs. The paper argues, pretty convincingly I think, that even a non-Turing complete language could still stimulate complex loops through repeated calls, hitting resource limits anyway. So the gas mechanism is seen as the more direct and robust solution.
Makes sense. Now, Ether itself, the currency, it's needed for liquidity, obviously, but also for those crucial gas fees. The white paper outlined the initial issuance, a sale, some for the foundation, early contributors, and then this idea of a permanent linear annual issuance to miners. Why linear? Why permanent?
That was an interesting choice. The justification given was multifaceted. A constant linear issuance, rather than one that halves like Bitcoin's, was argued to reduce wealth concentration over time. It gives a constant opportunity for newcomers to acquire Ether through mining or buying from miners. And while the absolute amount is constant, the percentage inflation rate still trends towards zero over the long run as the total supply grows. It also helps counteract Ether loss due to people losing keys, effectively stabilizing the circulating supply over very long time horizons. Plus, the paper mentioned future plans to move to proof of stake, which would drastically reduce the issuance needed for security anyway.
Right. PS changes the economic incentives entirely.
Exactly. And there was also this concept of a social contract, the idea that the community could, if needed, fund ongoing development even if the initial foundation disappeared.
Okay. Another big concern, especially looking at Bitcoin, was mining centralization. ASICs, specialized hardware, gave big players an edge. How did Ethereum plan to counter that?
That was definitely top of mind. Bitcoin's SHA-256 algorithm is very calculation-heavy, perfect for ASICs, which led to centralization in manufacturing and pools. Ethereum's initial plan was to use a proof-of-work algorithm, ETH, designed to be ASIC-resistant. The idea was to make it memory-hard, requiring lots of RAM access, making the hardware needed much closer to consumer-grade GPUs or CPUs. The design also aimed to require access to the blockchain state, effectively forcing miners to be full nodes, which could help decentralize the network further compared to Bitcoin's lightweight mining pools.
Interesting approach. Finally, the elephant in the room for any blockchain, scalability. Same issue as Bitcoin, right? Every transaction processed by every node, that doesn't scale to Visa levels easily.
No, it doesn't. That's the fundamental bottleneck. If Ethereum were to handle tens of thousands of transactions per second like Visa, the blockchain size would explode. The risk, again, is centralization. If only huge companies can afford the hardware to run a full node, the network loses its decentralized nature.
So what were the initial thoughts or mitigations mentioned in the white paper?
Well, besides the mining design potentially encouraging more full nodes, they pointed to the Patricia tree structure, allowing for state pruning, as we discussed. They also mentioned the possibility of future challenge response protocols. These would allow light clients to verify parts of the state more securely without trusting intermediate servers, even if they couldn't store the whole thing. It acknowledged the challenge, recognizing that true scalability would require further research and development beyond the initial launch. Decentralization versus scale is an ongoing tension.
So, wrapping up, we've journeyed from Bitcoin's elegant, but let's say specialized design for money, to Ethereum's incredibly ambitious vision, a programmable, decentralized world computer designed for almost any kind of application you could imagine coding. It's amazing to see how that 2014 white paper really laid the conceptual groundwork for so much that followed.
It truly did. It fundamentally shifted the conversation about what blockchain could be. It's not just about transactions anymore. It's about creating new ways to manage property, identity, data, organizations, complex agreements, even computation itself, building trust directly into the digital fabric.
Building trust into systems, not just transactions. That's a powerful takeaway. The deep dive really highlights the foundational thinking that sparked an entire ecosystem of innovation. So it leaves us with a final thought for you, the listener. If a blockchain can serve as the secure, verifiable base layer for nearly any digital agreement or application, what will you imagine building on it next?